Imagine trying to hover perfectly still while firing a garden hose in random directions. Physics says it's impossible. The water's momentum should send you tumbling. Yet right now, an object the size of a city block is doing exactly that in the darkness between worlds. 3I Atlas arrived from interstellar space, exhibiting behavior that violates our most basic understanding of how things move through the cosmos. It's actively venting material like any normal comet, but somehow avoiding the acceleration that should inevitably follow. Engineers call this the rocket effect, and it's never failed before. Tonight, we'll explore why this single anomaly might represent humanity's first encounter with technology not of this world. Journey with us to uncover how 3I Atlas just gave us the most compelling piece of evidence for alien intelligence we've ever detected. Part 1. The Impossible Object. 3I Atlas is venting gas like a comet, but its path isn't budging the way physics says it should. Picture this: an icy rock hurtling through the void, occasionally firing microscopic spray nozzles in random directions. According to everything we know about orbital mechanics, those tiny jets should act like thrusters, nudging the object's trajectory in measurable ways. Yet somehow, this interstellar visitor appears to be defying one of the most fundamental principles of spaceflight. Let's define our terms in 20 seconds flat. When astronomers track objects in space, they distinguish between gravity-only motion, the predictable dance of celestial bodies following Newton's laws, and what they call non-gravitational acceleration, or NGA. Think of NGA as those tiny speed and trajectory changes caused by outgassing steam from heating ice, or even the gentle pressure of sunlight itself. For most active comets, these forces are as reliable as clockwork. Gas escapes, momentum transfers, paths shift. It's rocket science in its purest form. But here's where 3I Atlas becomes genuinely perplexing. The Hubble Space Telescope has captured stunning images of its shroud of gas and dust, what astronomers call a coma. The James Webb Space Telescope has analysed its chemical fingerprint in unprecedented detail. Gemini South Observatory and the Very Large Telescope have tracked its evolving tail structures over weeks and months. Every instrument that's pointed at this object confirms the same startling reality. It's actively venting material into space. Yet when teams of astronomers run their precision calculations, fitting orbital models to months of positional measurements, something extraordinary emerges. Or rather, something extraordinary doesn't emerge. The non-gravitational acceleration that should be screaming from the data, that signature push from escaping gas, remains stubbornly at or below detection limits. Current orbit. Solutions have not reported a robust, peer-reviewed NGA detection. Only upper limits, only discussions, only the scientific equivalent of radio silence, where there should be a clear signal. This isn't just unusual. In the context of comet physics, it borders on impossible. Imagine watching a balloon slowly deflate while expecting it to drift across the room, only to see it hovering perfectly still. The gas is flowing, preferentially in certain directions according to telescope observations, yet the object isn't measurably drifting like a slow leak, pushing a spacecraft off course. Two interpretations have emerged from this puzzle, and they represent fundamentally different views of reality itself. The first suggests we're witnessing something natural but extraordinary, perhaps a massive nucleus that can absorb the momentum of escaping gas without flinching, or an unusually symmetric pattern of outgassing where jets balance each other with perfect precision. The second interpretation, whispered in research papers and debated in scientific forums, ventures into more speculative territory. What if we're observing artificial stabilization? What if something is actively minimizing detectable drift? It's crucial to understand that this second possibility comes from commentators and theorists pushing the boundaries of conventional thinking. It's not consensus science, not yet, but it's also not easily dismissed when we consider that 3I Atlas represents only the third confirmed interstellar visitor in recorded history. Every data point matters when you're studying messengers from the cosmic deep, objects that spent millions of years traversing the space between stars before gracing our solar system with their presence. The stakes couldn't be higher. This object won't linger in our neighborhood forever. With each passing day, it grows fainter as it retreats back toward interstellar space, carrying its secrets with it. We have a narrow window to unravel this mystery, before 3I Atlas fades into the cosmic background, leaving us with more questions than answers. Throughout this investigation, we'll maintain a clear distinction between what our telescopes have actually measured and what remains in the realm of speculation. The facts are extraordinary enough: visible activity without corresponding dynamical effects. But the implications, those stretch from the exotic physics of comet formation to the possibility that we're not alone in the universe. The discovery timeline reveals even more puzzles that demand explanation, including a mysterious early brightening and the first whispers that 3I Atlas might somehow be slowing down its activity in ways that contradict our models. Part 2. Discovery and Early Mysteries. The story of 3I Atlas begins not with a single moment of discovery, but with a cosmic game of hide-and-seek played across months of archived sky surveys. The earliest images, captured during routine recovery searches in May 2025, show nothing more than a faint point of light drifting against the stellar background. Just another anonymous speck in a universe filled with trillions of such specks. July 1st, 2025. The Atlas telescope in Chile, an automated sentinel designed to scan the heavens for potentially hazardous asteroids, captured something unusual, not because of what it saw, but because of how fast it was moving. Initial calculations suggested an object on a hyperbolic trajectory, the mathematical signature of something unbound by our sun's gravitational embrace. Within days, confirmation arrived from observatories around the world. Humanity had detected its third confirmed interstellar visitor. The direction of approach adds another layer to the mystery. 3I Atlas appeared to emerge from the direction of our galaxy's center, from the constellation Sagittarius, where stars crowd together in such dense fields that early measurements become exercises in precision threading needles. This cosmic traffic jam helps explain why initial estimates often shift and evolve as more data arrives. When you're trying to track a visitor from interstellar space against a backdrop of countless stellar neighbors, every photon matters. Context shapes everything in astronomy, so let's establish the crucial numbers that govern this encounter. At its closest approach to our Sun, scheduled for around October 30th, 2025, 3I Atlas will reach a distance of approximately 1.4 astronomical units. That's about 200 million kilometers, or roughly 1.5 times the distance from Earth to the Sun. From our home planet, it maintains an even more comfortable margin, never approaching closer than 1.7 to 1.8 astronomical units. This is emphatically not a threatening object. It poses no danger to Earth, no risk of collision, no cause for planetary defense protocols. But safety and scientific significance often travel different paths. The early photometry tells a story of rapid transformation. Soon after discovery, observers reported significant brightening as 3I Atlas developed its characteristic coma and began actively venting material. But here's where caution becomes essential. Precise brightening factors remain under investigation across multiple datasets. Was this purely a matter of growing activity as frozen gases began sublimating under solar heating, or did viewing geometry and the expanding coma contribute to the apparent magnitude changes? These questions illustrate why slowing down claims require careful verification rather than headlines. Hubble's iconic July 21st image revealed our first clear look at 3I Atlas in action. A distinct, sun-facing plume stretched from the nucleus, confirming active outgassing directed toward our star. More intriguingly, extremely faint features suggesting an anti-tail, material pointing toward the sun rather than away from it, appeared in the data. These ghostly structures evolved over subsequent weeks, eventually giving way to more conventional behavior. By August 27th, Gemini South Observatory captured images showing a clearer anti-solar tail, the familiar sight of a comet's dust being swept away from the sun by radiation pressure and solar wind. But that transition from unusual anti-tail features to normal tail development raises fascinating questions about the object's rotation, its surface properties, and the complex interplay between different types of ejected material. Let's pause to explain these tail geometries without drowning in technical jargon. An anti-tail isn't evidence of backwards physics or alien propulsion. It's a matter of perspective and orbital mechanics. When Earth, the comet and the Sun align in specific ways, we can see dust particles that were ejected weeks or months earlier and have since spread out along the object's orbital path. From our viewpoint, this creates the illusion of material pointing toward the Sun, when it's actually just the visible portion of a much larger debris sheet. The effect is unusual but entirely natural, observed in several solar system comets throughout history. Still, the timing and evolution of these features in 3I Atlas adds another piece to our growing puzzle. If activity patterns were this visually dramatic, creating plumes and evolving tail structures visible to our best telescopes, then the fundamental question returns with even greater force. Where is the corresponding non-gravitational acceleration? Why isn't this active, outgassing object being pushed around by its own emissions the way physics demands? This tension between visible activity and absent dynamics sets the stage for everything that follows. Because in astronomy, when the expected doesn't happen, that's often when the most interesting discoveries wait to be made. Part 3. What NGA means in practice. Picture yourself on a skateboard holding a slowly leaking water bottle. The escaping water creates a gentle but persistent push in the opposite direction, gradually accelerating you backward. This playground physics scales up beautifully to explain how comets and asteroids get nudged by their own emissions. Welcome to the rocket effect in miniature, the same principle that powers spacecraft and governs the orbital evolution of every active body in our solar system. But measuring this effect on objects millions of kilometers away requires extraordinary precision. Astronomers employ high-precision astrometry, tracking positions over weeks and months to detect tiny deviations from purely gravitational motion. They construct mathematical models that account for every known force: the Sun's pull, planetary perturbations, relativistic effects, and then search for systematic residuals that can't be explained by gravity alone. It's like trying to measure whether a distant ship is being pushed by a breeze by watching it through a telescope and timing its progress against the stars. The numbers involved are almost incomprehensibly small, yet they tell profound stories about the physics of small bodies in space. 2I/Borisov, our previous interstellar comet visitor from 2019, exhibited non-gravitational acceleration consistent with normal outgassing behavior, approximately 3.8 times 10 to the negative 7th meters per second squared when scaled to 2 astronomical units from the Sun. This might sound like nothing, but over months of observation, such tiny accelerations accumulate into measurable orbital changes. 1I/Oumuamua, our first confirmed interstellar visitor, presented the opposite extreme. Despite showing no visible gas or dust emissions, it demonstrated a much larger NGA of roughly 4.9 times 10 to the negative 6th meters per second squared at 1 astronomical unit from the Sun. This was 30 times larger than Borisov's. Acceleration, yet Oumuamua appeared completely inactive to our telescopes. The mystery of invisible forces pushing a seemingly dead rock sparked years of scientific debate and pushed the boundaries of theoretical explanations. For comparison, consider Comet 67P/Churyumov-Gerasimenko, exhaustively studied by the Rosetta mission. Direct measurements from spacecraft instruments confirmed exactly what orbital mechanics predicted. Outgassing produces measurable forces that alter trajectories in predictable ways. Jets of sublimating water and carbon dioxide created thrust vectors that mission planners had to account for when positioning the orbiting probe. Rosetta provided our ground truth calibration for how active comets should behave. Now we understand why symmetry becomes so crucial in this cosmic detective story. Imagine that water bottle experiment again, but this time with leaks pointing in multiple directions. If the streams are perfectly balanced, the forces cancel out and you remain stationary despite vigorous activity. Scale this up to a rotating comet nucleus with multiple active regions, and you can envision scenarios where dramatic outgassing produces minimal net acceleration. The key word is minimal, not zero. Perfect cancellation would be remarkable in itself. This brings us to 3I Atlas's current status in the annals of unusual objects. Spectroscopic observations confirm a carbon dioxide-rich coma, indicating substantial outgassing activity. Visual observations show evolving tail structures and plume features, yet no widely accepted, peer-reviewed detection of significant non-gravitational acceleration has emerged from the orbital analysis teams. The upper limits remain frustratingly low compared to the visible evidence of activity. We now have twin anomalies bookending the spectrum of expected behavior. Oumuamua showed us too much NGA without visible cause. 3I Atlas appears to show us visible cause without corresponding NGA. Both cases challenge our models of how small bodies should behave when they venture through the inner solar system, and both have captured the attention of scientists worldwide for precisely this reason. The implications stretch beyond mere curiosity. If we can't predict how interstellar visitors will behave when they encounter our sun's heating, how can we properly study them? How can we distinguish between natural variations in comet physics and potentially artificial influences? These questions become more pressing as we prepare for the next wave of discoveries that advanced survey telescopes promise to deliver. But first, we need to examine the chemical fingerprint that 3I Atlas is writing across the spectrum, because that signature contains clues that some researchers find deeply puzzling. Part 4. Nickel in the Coma. The Very Large Telescope in Chile's Atacama Desert has spent decades dissecting starlight to reveal the chemical secrets of distant worlds. When its X-shooter spectrograph turned toward 3I Atlas, it captured something genuinely puzzling, a chemical signature that challenges our understanding of how comets should behave. The spectrum revealed clear nickel emission lines, while iron remained conspicuously absent, creating a cosmic chemistry puzzle that demands explanation. In the vocabulary of astronomical spectroscopy, these are nickel-1 and iron-1 lines, neutral atoms of these metals excited by solar radiation and glowing at characteristic wavelengths. The detection of nickel without corresponding iron stands out because, in most comets observed throughout history, these two elements tend to appear together at broadly similar levels. They're metallurgical companions, forged in stellar furnaces and incorporated into planetary materials as partners rather than solo acts. The numbers paint the picture more precisely. Nickel emission lines appeared clearly in the spectrum, while iron remained below detection limits, creating an unusual chemical profile that requires explanation. Alongside the nickel, astronomers detected cyanide, CN molecules, with production rates that increase steadily as 3I Atlas approached the Sun. This behavior matches normal comet physics, but the metal signature does not. Several natural explanations remain under active investigation by planetary scientists worldwide. Space weathering could preferentially liberate nickel-bearing compounds such as nickel tetracarbonyl, NiCold, from the nucleus surface. Solar ultraviolet radiation would then photodissociate these molecules, freeing nickel atoms to glow in the characteristic emission lines. Different volatility pathways might explain why nickel appears before iron in the sublimation sequence. Grain size effects, surface composition variations, and thermal processing during the object's interstellar journey all offer potential solutions to this chemical conundrum. But some commentators have ventured into more speculative territory, suggesting that nickel without iron might mirror the erosion signature of nickel-based superalloys used in high-temperature engineering applications. These materials, designed to withstand extreme heat in jet engines and spacecraft propulsion systems, could theoretically shed nickel-rich particulates under operational stress. This interpretation transforms a chemistry puzzle into a technology signature, though it remains firmly in the realm of hypothesis rather than accepted scientific conclusion. The James Webb Space Telescope adds another layer to this chemical mystery, with observations that reveal 3I Atlas possesses one of the most unusual compositions ever measured in a comet. Its coma shows an extraordinarily high ratio of carbon dioxide to water, among the highest CO2 divided by H2O ratios detected in any comet studied to date. Water and carbon monoxide remain comparatively low, suggesting either formation near a carbon dioxide ice line in its birth system or a thermal. History, unlike most objects we've encountered. This chemical peculiarity might actually provide a natural explanation for the missing non-gravitational acceleration. Carbon dioxide sublimates more symmetrically than water ice, which tends to create directed jets from specific surface regions. If 3I Atlas is dominated by CO2 outgassing rather than H2O, its activity patterns might naturally produce more isotropic, that is, evenly distributed, thrust vectors. Multiple CO, two sources scattered across the surface, could create a complex pattern of forces that largely cancel each other out, leaving minimal net acceleration despite vigorous overall activity. This brings us to an interesting convergence of chemistry and dynamics. The same unusual composition that produces the puzzling nickel signature might also explain why this object appears to resist the rocket effect that governs normal comet behavior. Natural processes, rather than artificial intervention, could account for both anomalies simultaneously, yet questions persist. Why would an interstellar object have such unusual chemistry compared to solar system comets? Did it form in an environment unlike our local stellar neighborhood? Has its million-year journey between stars somehow altered its surface composition through cosmic ray bombardment or other space weathering processes? These questions highlight how much we still don't understand about the formation and evolution of planetary materials in other stellar systems. The chemical evidence forces us to confront the possibility that our models of comet composition, developed from decades of studying objects born in our own solar system, might not apply to visitors from elsewhere. 3I Atlas could be showing us what comets look like when they form around different types of stars, in different chemical environments, under different thermal conditions than anything we've previously encountered. If chemistry alone can't explain the absence of measurable thrust, perhaps the answer lies in sheer scale, the possibility that we're dealing with an object so massive that ordinary comet outgassing simply can't budge it. Part 5. The mass argument. Sometimes the simplest physics provides the most profound insights. The rocket equation that governs spacecraft propulsion also applies to comets. Thrust equals mass flow rate times exhaust velocity. Flip this relationship around, and if you can measure the thrust and estimate the gas flow, you can derive the mass. When researchers applied this logic to 3I Atlas, they arrived at a conclusion that challenges everything we thought we knew about interstellar visitors. The James Webb Space Telescope's NIRSPEC instrument observed 3I Atlas on August 6, 2025, providing unprecedented measurements of its carbon dioxide plume. The team derived gas production rates and outflow velocities with precision impossible from ground-based observations alone. These numbers, combined with the upper limits on observed non-gravitational acceleration from orbital fitting teams, paint a picture of an object that might be far more massive than its brightness suggests. One interpretation, advanced by researchers including Harvard's Abraham Loeb, combines the JWST outgassing data with the conspicuous absence of robust NGA detection to infer a nucleus mass of at least 3.3 times 10 to the 10th metric tons. To put this in perspective, that's roughly equivalent to the mass of a small mountain, compressed into what appears to be a relatively modest comet nucleus. The term anomalously massive begins to appear in research papers and conference presentations, scientific language for something that shouldn't exist according to our current understanding. If this mass estimate proves accurate, it would explain the missing non-gravitational acceleration through pure Newtonian physics. A sufficiently massive nucleus could absorb the momentum of ply, escaping gas without measurable deflection, like trying to push a cargo ship with a garden hose. The thrust is real, but the object simply has too much inertia to respond noticeably to forces that would send a typical comet tumbling off course. But mass estimates for distant objects remain frustratingly uncertain. Hubble imaging efforts continue working to constrain the nucleus size and albedo, the reflectivity that determines how much light it absorbs versus reflects. Coma brightness can mislead observers about the true size of the underlying solid nucleus, especially when that nucleus remains unresolved even by our most powerful telescopes. The difference between a large, dark object and a smaller, brighter one can amount to orders of magnitude in estimated mass. This uncertainty cuts to the heart of why 3I Atlas continues to puzzle researchers worldwide. If the mass is indeed anomalously high, we need to understand how interstellar space could forge objects so different from anything in our solar system. Dense cores of rock and metal? Compacted debris from some cosmic catastrophe? The formation mechanisms that could produce such massive dark nuclei remain unclear. Alternatively, if the mass proves more typical, we return to the original puzzle. Why doesn't visible activity produce measurable acceleration? The symmetry argument becomes more compelling, suggesting that the object's rotation and surface properties create a remarkably balanced pattern of outgassing that minimizes net thrust despite substantial total activity. Either explanation pushes the boundaries of our understanding. Anomalously massive objects challenge models of planetesimal formation and evolution. Perfectly balanced outgassing challenges the random, chaotic nature we typically associate with comet surface activity. Both possibilities suggest that interstellar visitors might operate according to different rules than the objects we've studied for centuries in our own cosmic neighborhood. The mass argument also raises intriguing questions about detection methods and observational bias. Have we been missing massive dark objects simply because they don't brighten dramatically when they approach the Sun? Could there be a population of interstellar visitors passing through undetected because they lack the dramatic outgassing that makes objects like 3I Atlas visible to our surveys? These questions become more pressing when we consider that we've now detected two highly unusual interstellar objects in just 8 years, Oumuamua and 3I Atlas, both displaying behaviors that challenge conventional comet physics in opposite directions. This track record suggests either remarkable coincidence or systematic gaps in our understanding of how objects behave when they venture between stars. The precedent set by our first interstellar visitor adds crucial context to this mass mystery, because Oumuamua demonstrated that the impossible can sometimes become merely improbable with enough careful analysis. Part 6. Lessons from Oumuamua. October 19th, 2017. Pan-STARRS, one telescope in Hawaii detected what initially appeared to be a faint asteroid, but within days astronomers realized they were witnessing something extraordinary. Humanity's first confirmed visitor from interstellar space. 1I/Oumuamua, Hawaiian for scout or messenger, would challenge our understanding of solar system dynamics in ways that still reverberate through planetary science today. The initial observations revealed an object unlike anything previously catalogued. No visible coma, no dust tail, no signs of the outgassing activity that characterizes comets when they approach the Sun. To all appearances, Oumuamua looked like a dead rock tumbling through space, following a hyperbolic trajectory that confirmed its interstellar origin. Yet when astronomers began precision orbit determinations, something extraordinary emerged from the pooled astrometric data. Oumuamua was accelerating. The magnitude of this non-gravitational acceleration measured approximately 4.9 times 10 to the -6th meters per second squared at 1 astronomical unit from the Sun, with a characteristic inverse square dependence on distance that suggested radiation pressure or outgassing-like physics. But here's what made this discovery so puzzling. The acceleration was statistically significant to 30 standard deviations, meaning the probability of this being a measurement error was essentially zero, yet no visible outgassing or dust emission could account for such a strong force. This created what astronomers diplomatically call an interesting problem. How do you accelerate a seemingly inert object without any visible mechanism for creating thrust? The physics seem to demand some form of mass ejection, whether gas or dust, to provide the momentum transfer necessary for orbital changes. Yet every telescope that observed Oumuamua failed to detect the expected emissions. The controversy that followed spawned dozens of research papers exploring increasingly exotic possibilities. Could solar radiation pressure alone account for the acceleration if the object had an unusually high area-to-mass ratio? Might it be venting transparent gas that escaped detection by conventional spectroscopy? Did its unusual elongated shape somehow amplify thermal re-radiation effects? Each proposed solution required assumptions that stretched conventional comet physics to its breaking point. Perhaps most intriguingly, some researchers suggested that Oumuamua might not be a natural object at all. The combination of its unusual trajectory, extreme aspect ratio, and unexplained acceleration led to speculation about artificial origins, a possibility that captured public imagination while dividing the scientific community. Headlines proclaimed everything from alien probes to solar sails, though peer-reviewed papers approached such possibilities with appropriate caution. The narrative significance of Oumuamua extends beyond its individual characteristics. to what it represents for our understanding of interstellar visitors. Here was an object displaying too much NGA without visible cause, the exact opposite of what we observe with 3I Atlas, which shows visible cause without much NGA. These twin anomalies bracket the expected range of behavior and suggest that interstellar space might harbor objects that operate according to different physical principles than solar system natives. Statistical arguments add weight to this puzzle. In 8 years, we've confirmed exactly 3 interstellar visitors, and 2 of them display highly unusual dynamics. Either we've been remarkably unlucky in our sampling, or unusual behavior might be more common among interstellar objects than our solar system experience would suggest. This raises profound questions about the diversity of planetary materials and formation processes operating around other stars. The Oumuamua legacy also demonstrates how anomalous observations drive scientific progress. The intense scrutiny, triggered by its unusual behavior, led to improved theoretical models, better observational techniques, and renewed interest in interstellar visitor detection programs. What began as an inexplicable acceleration became a catalyst for advancing our understanding of small body physics, radiation pressure effects, and the complex interplay between thermal processes and orbital dynamics. Most importantly, Oumuamua established the template for approaching anomalous interstellar objects with scientific rigor. Extraordinary claims require extraordinary evidence, but they also demand extraordinary attention to detail and willingness to consider possibilities that challenge conventional wisdom. The object forced astronomers to expand their theoretical frameworks while maintaining strict standards for evidence and reproducibility. This experience proves invaluable as we grapple with 3I Atlas and its opposite extreme behavior. The lessons learned from 8 years of Oumuamua analysis, from careful astrometric reduction to thermal modeling to consideration of exotic possibilities, provide the methodological foundation for understanding our latest interstellar visitor. Yet there's another lesson worth extracting from our brief catalogue of interstellar encounters. Sometimes the most valuable insights come not from the anomalies, but from the objects that behave exactly as expected. Part 7. Lessons from 2. I Divided by Borisov. August 30th, 2019. Crimean amateur astronomer Gennady Borisov spotted what he initially thought might be a comet in the constellation Lynx. Within weeks, orbital calculations confirmed something remarkable. 2I/Borisov represented humanity's second confirmed interstellar visitor, but unlike its predecessor Oumuamua, this object behaved exactly like a comet should behave. It arrived as a cosmic control experiment, demonstrating that interstellar doesn't necessarily mean anomalous. Borisov's behavior provided textbook confirmation of comet physics operating on an interstellar scale. As it approached the sun, water and other volatiles began sublimating from its nucleus, creating the characteristic coma and tail visible to telescopes worldwide. Spectroscopic analysis revealed familiar chemistry, water vapor, carbon monoxide, and other molecules common in solar system comets. Its color, composition, and activity patterns all fell within the normal range of expectations for a pristine comet experiencing its first close encounter with stellar heating. Most importantly for our current discussion, Borisov exhibited non-gravitational acceleration that matched theoretical predictions with reassuring precision. Orbital analysts measured approximately 3.8 times 10 to the negative 7th meters per second squared at 2 astronomical units from the Sun, the value entirely consistent with the measured gas production rates and outflow velocities. The rocket effect worked exactly as physics textbooks suggested it should. This convergence of observation and theory provided crucial validation for our understanding of comet dynamics. When astronomers calculated the momentum transfer from escaping gas and compared it to the observed orbital perturbations, the numbers aligned beautifully. Borisov demonstrated that the fundamental physics governing small body behavior remains constant, regardless of whether objects formed in our solar system or spent millions of years drifting through interstellar space. The implications extend far beyond a single successful prediction. Borisov proved that interstellar origin doesn't automatically imply exotic behavior or mysterious physics. Objects from other stellar systems can follow the same natural laws, exhibit the same chemical processes, and respond to solar heating in predictable ways. This normal behavior makes the anomalies displayed by Oumuamua and 3I Atlas even more significant by contrast. Consider what this means for our cosmic perspective. Borisov spent approximately 1 million years travelling between stars after being ejected from its birth system. Yet, when it finally encountered our Sun, it activated like any comet experiencing perihelion passage. The ice was still ice, the dust was still dust, and the physics of sublimation proceeded according to laboratory predictions. Interstellar space preserves these objects rather than transforming them beyond recognition. This preservation has profound implications for astrobiology and comparative planetology. If objects like Borisov retain their original chemistry and structure across interstellar distances, they serve as messengers carrying direct samples of other stellar systems. Every spectroscopic measurement, every chemical analysis, provides insights into the conditions and processes operating around distant stars. Billions of years ago, when these objects first formed, the statistical context becomes crucial here. 3 confirmed interstellar visitors, with behavior ranging from completely normal, Borisov, to moderately anomalous, Oumuamua, to puzzling in different ways, 3I Atlas. This small sample suggests that while most interstellar objects might behave predictably, a significant fraction display characteristics that challenge our theoretical frameworks. Borisov's exemplary behavior also validates our observational techniques and analysis methods. When the physics works as expected, it confirms that our instruments, models, and theoretical understanding can successfully predict and explain what we observe. This gives us confidence when applying the same techniques to more unusual objects like 3I Atlas. If the methods work for normal cases, discrepancies in anomalous cases likely represent real physical differences rather than systematic errors. The lesson extends to future discoveries as well. The upcoming Vera Rubin Observatory will multiply our detection rate of interstellar visitors by orders of magnitude, potentially delivering dozens or hundreds of such objects for study. Borisov's example suggests that many of these discoveries will prove mundane from a physics standpoint, valuable for comparative planetology, but unremarkable in terms of fundamental dynamics. This normal population will provide the statistical baseline necessary for identifying truly anomalous objects that demand special attention. Yet even within our own solar system, where we've had centuries to study comet behavior in detail, the relationship between activity and acceleration isn't always straightforward. Large comets with dramatic outgassing can still exhibit significant non-gravitational effects, reminding us that mass alone doesn't determine whether an object will respond to its own emissions. Part 8. Other comet benchmarks. 67P/Churyumov-Gerasimenko measures just 4 kilometers across at its widest point, yet when the European Space Agency's Rosetta mission arrived for its unprecedented 12-year escort mission, this modest comet demonstrated the rocket effect with classroom precision. Direct measurements from instruments positioned mere kilometers from the nucleus confirmed every aspect of theoretical predictions. Outgassing creates forces alter orbits, and the magnitude of these changes depends predictably on gas production rates, exhaust velocities, and nucleus mass. Rosetta's in-situ observations eliminated any ambiguity about the physical mechanism behind non-gravitational acceleration. High-resolution cameras captured jets of sublimating material erupting from specific surface features. Mass spectrometers analyzed the chemical composition of the gas plumes. Dust detectors recorded particle impacts from debris lifted off the surface. When mission planners calculated the cumulative thrust from all this activity, their predictions matched the observed orbital perturbations of the spacecraft itself with extraordinary accuracy. This microscopic validation of comet physics provides the foundation for understanding how larger objects should behave. Scale up the nucleus size, increase the gas production rates, and the same fundamental relationship between outgassing and acceleration should apply. Yet size introduces complications that pure physics doesn't always capture cleanly. Consider Comet Hale-Bopp, one of the largest and most spectacular comets of recent decades. During its 1997 apparition, this giant displayed a nucleus estimated at 60 kilometers in diameter, roughly 15 times larger than Churyumov-Gerasimenko. Despite its massive size, Hale-Bopp still exhibited measurable non-gravitational acceleration as it approached the Sun, proving that even very large comets cannot entirely resist the rocket effect of their own emissions. The lesson resonates directly with our 3I Atlas mystery. Mass provides inertia that dampens acceleration, but it doesn't eliminate the effect entirely unless the object reaches truly extraordinary scales. For perspective, even a nucleus massing 10 to the 10th metric tons, the anomalously massive estimate proposed for 3I Atlas, should still show some measurable response to asymmetric outgassing if the jets are sufficiently powerful and directionally biased. This brings us to the critical importance of symmetry and vent geometry in determining net acceleration. Computer models of comet outgassing, validated against spacecraft observations, demonstrate that the spatial distribution of active areas determines whether individual jets reinforce each other or cancel out. A nucleus with randomly distributed vents might experience minimal net thrust even while producing dramatic visual displays of activity. Astronomers encode these effects in their orbital solutions using what they call a 1, a 2, and a 3 parameters, the mathematical terms that capture how non-gravitational forces vary with distance from the Sun and position in the orbit. Early in an object's apparition, these parameters carry large uncertainties simply because insufficient time has elapsed to accumulate the tiny positional changes that reveal systematic departures from pure gravitational motion. The temporal aspect cannot be overstated. Measuring non-gravitational acceleration requires patient accumulation of astrometric data over months or years. Objects discovered late in their solar approach, like many interstellar visitors, provide limited observational baselines that constrain the precision of dynamical analysis. What appears to be no acceleration might simply reflect not enough time to detect small acceleration, given the measurement uncertainties involved. Yet when we place 3I Atlas within this broader context of comet behavior, its combination of visible activity and undetected acceleration remains statistically unusual. Most active comets discovered in our solar system exhibit measurable dynamical effects within weeks or months of developing significant comas. The absence of such effects, despite clear evidence of ongoing outgassing, continues to set this object apart from both interstellar and local populations. The benchmarks established by decades of comet observations create expectations that 3I Atlas appears to violate. Whether through unusual mass, perfect symmetry, or some other physical mechanism, this object challenges our ability to predict how active bodies should behave when they encounter stellar heating. Such challenges often herald the most significant scientific discoveries, moments when nature reveals phenomena that textbooks haven't yet incorporated. But what if the explanation lies not in exotic physics or unusual formation scenarios, but in conscious intervention? The speculative possibility of artificial stabilization deserves careful examination, if only to understand why some researchers consider it worthy of serious discussion. Part 9. The Artificial Control Hypothesis. In the careful language of peer-reviewed science, extraordinary hypotheses receive extraordinary scrutiny, but they also receive consideration proportional to the quality of evidence that supports them. The artificial control hypothesis for 3I Atlas falls into this rarefied category, speculative enough to raise eyebrows, yet grounded in sufficient anomalous observations that dismissing it entirely might constitute intellectual negligence. Let's examine this possibility with the scientific rigor it demands while maintaining clear distinctions between speculation and established fact. The core premise rests on a simple engineering question. If you wanted to send a probe through interstellar space while minimizing detectable signatures of artificial propulsion, how might you design such a system? The answer involves active stabilization using small thrusters or reaction control systems to counteract the random forces that would otherwise create detectable trajectory changes. Cold gas microthrusters could provide precise thrust in opposition to natural outgassing. Symmetric reaction control systems might balance asymmetric gas jets. Momentum wheels, coupled with low thrust venting, could maintain attitude while eliminating net acceleration. Smart materials might even adjust surface properties to control heating patterns and gas emission directions. These aren't fantasy technologies. Human spacecraft have employed similar systems for decades. The International Space Station uses reaction control thrusters to counteract atmospheric drag. Deep space probes carry attitude control systems to maintain pointing accuracy, despite solar radiation pressure and thermal effects. The engineering principles exist. The question becomes one of scale, sophistication, and motivation. Consider the nickel without iron signature that has puzzled spectroscopists analyzing 3I Atlas emissions. In terrestrial engineering applications, nickel-based superalloys represent the gold standard for extreme temperature environments. Jet engines, rocket nozzles, and spacecraft propulsion systems all rely on materials designed to withstand temperatures that would vaporize conventional metals. Under operational stress, these superalloys do indeed shed nickel-rich particulates through normal wear processes. Could we be observing the erosion signature of advanced propulsion systems? The VLT paper documenting the nickel detection offers natural explanations involving space weathering and photodissociation chemistry, but some commentators have noted the intriguing parallel to high-temperature engine wear patterns. This interpretation transforms a chemical curiosity into potential technology identification, though it remains firmly in speculative territory rather than established science. Abraham Loeb's mass analysis adds another dimension to this discussion. If 3I Atlas indeed masses 3.3 times 10 to the 10th metric tons or more, equivalent to a small mountain, then we're potentially dealing with something built on scales that dwarf human engineering projects. Such mass could be interpreted as natural density concentration or as the signature of a constructed object designed for long-duration interstellar transit. The ambiguity inherent in mass estimates from photometric data means both interpretations remain viable pending better observational constraints. The trajectory characteristics of 3I Atlas have also attracted speculative attention. Some analyses suggest the object's path shows signs of deliberate navigation, maintaining specific orientations relative to the ecliptic plane, approaching from directions that optimize solar energy collection, and following trajectories that facilitate extended observation opportunities. These patterns could represent natural orbital mechanics, operating on objects ejected from other stellar systems, but they could also indicate intentional course corrections designed to maximize scientific return from a reconnaissance mission. More provocative suggestions have emerged from preprint servers and specialized blogs, including claims that 3I Atlas might represent what science fiction has termed dark forest technology, probes designed to study other civilizations while maintaining minimal detectability. These ideas venture far beyond mainstream scientific discourse, but they reflect the cultural impact of truly anomalous interstellar visitors on public imagination and speculative thinking. The artificial control hypothesis demands extraordinary evidence precisely because it makes extraordinary claims about the nature of intelligence in the universe. Demonstrating artificial origins would require multiple lines of converging evidence, systematic departures from natural physics that resist all conventional explanations, technological signatures that cannot be produced by known geological or chemical processes, and behavioral patterns that suggest purposeful control rather than random natural forces. Currently, 3I Atlas exhibits intriguing anomalies, but falls short of meeting these stringent evidentiary standards. The missing non-gravitational acceleration could reflect natural processes we don't yet understand. The unusual chemistry might result from formation conditions unlike anything in our solar system. The apparent mass concentration could represent natural density variations rather than artificial construction. Yet the hypothesis serves an important scientific function by expanding our investigative framework beyond purely natural explanations. If we restrict our analysis to conventional comet physics, we might miss signatures that indicate artificial origins should they actually exist. The history of astronomy includes numerous cases where seemingly impossible observations eventually yielded revolutionary insights about natural processes and occasionally about phenomena that challenged fundamental assumptions about reality itself. The key lies in maintaining appropriate skepticism while avoiding premature closure. Extraordinary hypotheses deserve serious analysis when supported by high-quality observations. but they also require extraordinary standards of proof before acceptance. 3I Atlas provides sufficient anomalies to warrant expanded theoretical consideration while falling short of definitive evidence for any particular exotic explanation. Before drawing conclusions about artificial origins, we need to examine what our most sophisticated instruments actually reveal about this object's stability, chemistry, and behavior patterns when subjected to detailed spectroscopic and imaging analysis. Part 10. Spectral Curiosities and Stability. The James Webb Space Telescope's near-spec instrument doesn't just collect light, it dissects it with surgical precision, revealing the molecular fingerprints that tell stories of cosmic chemistry spanning billions of years. When this extraordinary machine focused on 3I Atlas during its August 6, 2025 observation run, the resulting spectrum painted a portrait of an object unlike any comet previously studied in detail. The most striking feature dominates the near-infrared wavelengths, where carbon dioxide molecules absorb and re-emit photons with characteristic signatures. 3I Atlas exhibits one of the highest CO2 to H2O ratios ever measured in any comet, solar system or otherwise. While most comets show water as their dominant volatile, this interstellar visitor appears powered primarily by carbon dioxide sublimation, with water vapor and carbon monoxide playing distinctly secondary roles in its activity patterns. This chemical dominance suggests formation scenarios that challenge our understanding of typical comet compositions. Most objects in our solar system formed in regions where water ice condensed readily, creating the characteristic ice-rock mixtures we observe in periodic comets. But 3I Atlas appears to have originated in an environment where carbon dioxide dominated the volatile inventory, perhaps near a CO2 ice line around a different type of star, or in a protoplanetary disk with unusual chemical gradients. The implications for outgassing symmetry become immediately apparent. Water ice tends to concentrate in specific regions of comet nuclei, often associated with geological features or preferentially heated areas that create directed jets visible in spacecraft images. Carbon dioxide, by contrast, typically sublimates more uniformly across the surface, creating what physicists call isotropic outgassing patterns. If 3I Atlas is indeed CO2 dominated, its emissions might naturally produce a more balanced thrust profile that minimizes net acceleration despite substantial total activity. Hubble Space Telescope imaging chronicles the visual evolution of this unusual object across multiple wavelengths and observation epochs. The July 21st image captured a distinct sun-facing plume stretching from the nucleus, confirming active gas emission directed toward our star rather than randomly distributed. More intriguingly, extremely faint features suggested an anti-tail, material pointing sunward rather than away, that defied simple interpretation but fell within the range of natural phenomena observed in solar system comets under specific geometric conditions. By late August, Gemini South Observatory documented the transition to more conventional tail development, with material clearly streaming away from the Sun in response to radiation pressure and solar wind interactions. This evolution from unusual anti-tail features to normal comet behavior provides important constraints on the object's rotation period, surface properties, and the complex dynamics governing how different sized particles respond to solar forces over time. The Very Large Telescope's continued spectroscopic monitoring reveals the temporal dimension of 3I Atlas's chemical activity. Nickel and cyanide production rates increased steadily as the object approached perihelion, exactly matching the behavior expected from increasing solar heating. Iron remained below detection thresholds throughout this period, creating the persistent nickel without iron signature that continues to puzzle researchers seeking natural explanations for this unusual abundance pattern. These observations establish a crucial baseline for evaluating stability claims. Despite months of active outgassing, evolving tail structures, and rising production rates of multiple chemical species, the publicly discussed non-gravitational acceleration measurements remain at or below detection thresholds in peer-reviewed orbital solutions. This persistence of low or undetected dynamical effects, combined with clear evidence of ongoing material loss, represents the core anomaly that drives continued scientific interest. Natural modeling efforts have explored multiple scenarios for achieving this apparent stability. Computer simulations suggest that symmetric outgassing fields, combined with specific particle size distributions and rotational states, could indeed minimize net thrust while producing substantial visual activity. The challenge lies in explaining why 3I Atlas appears to achieve such precise balance when most active comets exhibit measurable acceleration within weeks of developing significant comas. The rotational dynamics add another layer of complexity. Objects tumbling through space typically expose different surface regions to solar heating in cyclical patterns, creating time-variable outgassing that produces characteristic acceleration signatures. If 3I Atlas maintains unusually stable orientation or possesses surface composition that minimizes rotational effects, this could contribute to the apparent dynamical stability that sets it apart from typical comet behavior. Temperature modeling based on the observed chemical emissions suggests surface conditions consistent with normal solar heating at its current distance. There's no evidence for internal heat sources, exotic thermal processes, or artificial temperature regulation that might indicate non-natural origins. The chemistry responds predictably to increasing solar flux, following well-understood sublimation physics despite the unusual abundance ratios. Yet questions remain about the long-term implications of these observations. As 3I Atlas continues its approach toward perihelion in late October, will the activity patterns maintain their apparent stability? Will increased heating finally overcome whatever mechanism prevents measurable acceleration? Or will this object continue challenging our understanding of comet physics, all the way to closest approach and beyond? The answers could reshape how we think about interstellar visitors, the diversity of planetary formation processes operating around other stars, and the fundamental relationship between outgassing activity and orbital dynamics. But first, we need to consider why these questions matter beyond pure scientific curiosity, how the study of anomalous interstellar objects might transform our search for intelligence elsewhere in the universe. Part 11. Why this matters to SETI. For 70 years, humanity has listened to the cosmos with increasingly sophisticated radio telescopes, hoping to detect the electromagnetic whisper that would confirm we're not alone. From the pioneering Project Ozma in 1960 to today's Breakthrough Listen initiative, the search for extraterrestrial intelligence has focused primarily on intentional signals, deliberate communications transmitted across interstellar distances by technological civilizations. But 3I Atlas suggests we might need to expand this paradigm to include accidental discoveries hiding in plain sight. The traditional SETI approach assumes that advanced civilizations will advertise their presence through powerful radio or optical beacons, essentially cosmic lighthouses sweeping through space to announce their existence to anyone capable of receiving the signal. This philosophy produced the iconic Arecibo message, transmitted in 1974, a demonstration of humanity's own beacon-building capabilities. It drives current surveys that monitor millions of stars for artificial signals across vast swaths of the electromagnetic spectrum. Yet this methodology contains an implicit assumption that might limit its effectiveness. It presupposes that extraterrestrial intelligence will choose to broadcast detectable signals rather than maintaining what science fiction has termed radio silence. If advanced civilizations prefer stealth to advertisement, whether for security, efficiency, or philosophical reasons, then traditional SETI techniques might systematically overlook evidence of their activities. Enter the complementary approach suggested by anomalous interstellar visitors like 3I Atlas. Instead of waiting for deliberate signals, this methodology involves studying naturally occurring phenomena for signatures that resist conventional explanation. Physical objects passing through our solar system carry information about their origins, compositions, and histories that no amount of electromagnetic jamming can obscure. If some of these objects prove to be artificial constructs rather than natural formations, they represent a form of evidence that doesn't depend on the intentions or communication strategies of their creators. This investigative framework operates on different timescales and methodologies than traditional radio SETI. Rather than continuous monitoring for fleeting signals, it requires rapid response to newly discovered objects during their brief passage through observable space. Rather than pattern recognition in electromagnetic data streams, It demands comprehensive analysis of orbital mechanics, spectroscopy, and photometry to distinguish artificial from natural phenomena. The statistical argument for this approach grows stronger with each anomalous interstellar detection. In just 8 years, we've identified 3 confirmed visitors from interstellar space: Oumuamua, Borisov, and 3I Atlas, and 2 of these objects display characteristics that challenge conventional explanations. Either we've been remarkably unlucky in our sampling, or unusual behavior might be common enough among interstellar objects to warrant systematic investigation, rather than case-by-case analysis. Consider the implications if even a small fraction of interstellar visitors prove to be artificial constructs. Reconnaissance probes launched by curious civilizations, automated surveys documenting stellar system properties, or even discarded infrastructure from technological species could be passing through our neighborhood on a regular basis. Current detection methods, optimized for natural objects following predictable orbits, might systematically miss artificial objects, employing stealth technologies or unusual propulsion systems. The philosophy underlying this expanded SETI approach acknowledges that advanced civilizations might prefer subtlety to advertisement. Rather than broadcasting their locations to potentially hostile neighbors, they might conduct reconnaissance using sophisticated probes designed to gather intelligence while maintaining plausible deniability as natural phenomena. Such objects would carry minimal electromagnetic signatures, follow trajectories that mimic natural dynamics, and employ technologies indistinguishable from advanced chemistry or physics. 3I Atlas fits this profile almost perfectly, anomalous enough to attract scientific attention, yet sufficiently ambiguous to permit natural explanations for every observed characteristic. If this represents intentional design rather than cosmic coincidence, it suggests a level of technological sophistication that makes traditional SETI assumptions appear anthropocentric and limited. The integration of interstellar object studies with traditional SETI methodologies creates a more comprehensive search strategy that doesn't depend entirely on the communication preferences of hypothetical extraterrestrial civilizations. Radio surveys continue monitoring for intentional signals, while rapid response campaigns investigate physical visitors for signs of artificial origins. This 2-track approach maximizes the probability of detection while minimizing the risk of false negatives due to incorrect assumptions about alien behavior. But implementing this expanded search strategy requires unprecedented coordination between astronomical surveys, space agencies, and research institutions worldwide. The brief visibility windows of interstellar visitors demand rapid telescope allocation, immediate spectroscopic follow-up, and real-time analysis capabilities that push the limits of current observational infrastructure. The next few months will prove crucial for testing these concepts, as 3I Atlas approaches its closest point to the Sun, potentially revealing new details about its composition, structure, and behavior that could shift the balance between natural and artificial explanations. Part 12. Observational windows ahead. The cosmic ballet proceeds according to precise mathematical choreography, and for 3I Atlas, the most important performance approaches its climax. October 30th, 2025 marks the object's perihelion passage, its closest approach to our Sun, at approximately 1.4 astronomical units. This encounter represents our best and perhaps final opportunity to extract definitive answers about this enigmatic interstellar visitor before it fades back into the cosmic deep. Orbital geometry governs everything in observational astronomy, and the changing angles between Earth, 3I Atlas, and the Sun will dramatically alter our viewing perspective over the coming weeks. As the object swings around perihelion, different surface regions will experience peak solar heating, potentially triggering new outgassing patterns or revealing compositional variations across the nucleus. If artificial systems are indeed maintaining trajectory stability, increased thermal stress might finally overwhelm their capabilities and produce detectable acceleration signatures. The enhanced solar flux at perihelion distance will also amplify spectroscopic signals, making faint emission lines more readily detectable and enabling precision measurements of isotopic ratios that could distinguish between natural and artificial material sources. Elements present in trace quantities might finally exceed detection thresholds, potentially resolving the mysterious nickel without iron abundance pattern that has puzzled researchers since. The first VLT observations. Mars presents an intriguing observational opportunity during early October, when several active orbiters will enjoy unique viewing geometry impossible to achieve from Earth-based telescopes. The Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express could potentially observe 3I Atlas from angles that reveal details about its nucleus shape, rotation state, and activity patterns invisible from our terrestrial perspective. These observations remain dependent on spacecraft scheduling priorities and technical feasibility assessments currently under discussion at mission control centers worldwide. More ambitious possibilities include opportunistic observations from deep space missions like Juno at Jupiter, ESA's JUICE probe, or NASA's Psyche asteroid mission. While none of these spacecraft were designed for interstellar visitor observations, their unique vantage points and sophisticated instrument packages could provide unprecedented multi-angle views of 3I Atlas during its perihelion passage. Such observations would require complex trajectory calculations and instrument calibrations, but the scientific return could justify the operational complexity involved. The key question driving all these observational strategies centers on what new data would definitively resolve the natural versus artificial debate. 3 specific types of measurements could shift the evidentiary balance dramatically. First, a statistically significant non-gravitational acceleration detection that correlates directly with measured outgassing would strongly support natural explanations by confirming that rocket physics operates normally for this object, despite its other anomalous characteristics. Conversely, persistent, low or undetected acceleration in the face of intensifying activity patterns would strengthen the anomaly narrative, particularly if detailed modeling could rule out plausible natural mechanisms for achieving such dynamical stability. The precision required for such measurements pushes current astrometric capabilities to their limits, demanding careful error analysis and multiple independent confirmations from different observational teams. Perhaps most importantly, resolved imaging of the nucleus itself could provide direct constraints on size, shape, and surface properties that would eliminate much of the uncertainty surrounding mass estimates and thermal modeling. If 3I Atlas proves to have normal density and composition despite its unusual behavior, natural explanations become more compelling. If imaging reveals unexpectedly high density, unusual geometry, or surface features inconsistent with natural formation, the artificial hypothesis gains credibility. The media landscape surrounding 3I Atlas illustrates both the opportunities and challenges inherent in studying potentially anomalous phenomena. Some outlets and commentators have embraced speculative interpretations, generating headlines about alien probes and interstellar visitors that capture public imagination, while potentially misleading audiences about the current state of scientific evidence. NASA and mainstream astronomical organizations have consistently emphasized natural explanations and the absence of any threat to Earth, maintaining the careful tone appropriate for ongoing research rather than settled conclusions. This tension between scientific caution and public fascination reflects deeper questions about how society should approach potentially transformative discoveries. Premature claims about artificial origins could damage credibility and funding for legitimate research programs. Excessive conservatism, however, might cause us to miss genuine signatures of non-terrestrial intelligence by dismissing anomalous observations too quickly. The resolution of these questions depends critically on maintaining the observational campaign through perihelion and beyond, extracting maximum scientific value from this rare opportunity to study an active interstellar visitor at close range. But even if 3I Atlas ultimately proves natural in origin, its discovery has already catalyzed improvements in our detection and analysis capabilities that will prove invaluable when the next mysterious visitor arrives. Part 13. The Vera Rubin Era. The Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory atop Cerro Pachón in Chile, will transform our understanding of the dynamic universe beginning in 2025. Every 3 nights, this revolutionary facility will image the entire southern sky to unprecedented depth, creating a time-lapse movie of cosmic evolution that spans a decade of continuous observations. For interstellar visitor research, This capability represents a quantum leap that will multiply discovery rates by orders of magnitude. Current interstellar object detection relies heavily on serendipity and the dedicated efforts of surveys like ATLAS, Linear, and Catalina Sky Survey. These programs have proven remarkably successful at finding unusual objects, but their sensitivity and sky coverage limits mean that we likely miss many faint, fast-moving visitors that pass through our solar system undetected. Rubin's combination of wide field coverage, deep limiting magnitudes, and rapid cadence will dramatically expand our ability to catch interstellar visitors during their brief transit through observable space. The numbers illustrate the transformative potential. Current surveys detect perhaps one interstellar visitor every few years, providing a sample size barely adequate for statistical analysis of their properties and behavior patterns. Rubin projections suggest we might discover dozens of such objects annually once the survey reaches full operational capacity, creating datasets rich enough to distinguish between normal variations and genuinely anomalous characteristics. Early detection capabilities become crucial for maximizing scientific return from each discovery. By identifying interstellar visitors months or years before perihelion passage, Rubin will provide time for comprehensive follow-up campaigns using the world's largest telescopes. Spectroscopic analysis, astrometric monitoring, and even spacecraft mission planning become feasible when working with extended lead times rather than the rushed observations that characterized our responses to Oumuamua and 3I Atlas. The pipeline from detection to characterization represents a logistical challenge that will require unprecedented coordination across the global astronomical community. Automated systems must identify candidate interstellar objects from millions of nightly detections, triggering immediate alerts to follow-up networks equipped with specialized instruments for rapid spectroscopy and precise astrometry. This real-time analysis capability will distinguish the Rubin era from previous decades, when discoveries often went unrecognized until weeks or months after initial detection. Statistical analysis becomes possible when sample sizes grow from individual cases to population studies. Are unusual chemical compositions like 3I Atlas's CO2 dominated spectrum common among interstellar visitors, or do they represent rare exceptions? Do most objects from interstellar space exhibit normal comet behavior like Borisov, or are anomalous dynamics more prevalent than our limited sample suggests? These questions require dozens or hundreds of well-characterized objects to answer definitively. The implications for SETI research grow proportionally with discovery rates. If even a small percentage of interstellar visitors prove to be artificial constructs, rapid detection and comprehensive analysis could provide the first confirmed evidence of non-terrestrial technology. Conversely, if extensive surveys reveal that all interstellar objects behave according to natural physical laws, this would place important constraints on the prevalence and detection strategies of hypothetical extraterrestrial civilizations. Mission feasibility studies for intercepting interstellar visitors become practical when working with years rather than months of advance warning. Small, dedicated spacecraft could potentially rendezvous with particularly interesting objects, providing in situ measurements impossible to achieve with Earth-based telescopes. Such missions would require rapid development and launch capabilities, but the scientific return from direct sampling of interstellar material could justify the technical challenges involved. The Rubin era also promises to reveal whether 3I Atlas represents a genuine anomaly or simply the most thoroughly studied example of a common phenomenon. If similar objects with unusual chemical signatures and anomalous dynamics appear regularly in the data stream, this would suggest that our theoretical understanding of comet physics requires substantial revision. If 3I Atlas proves unique among dozens of well-characterized interstellar visitors, its anomalous nature becomes more significant and potentially indicative of non-natural origins. Educational and public outreach opportunities multiply when discoveries occur regularly rather than sporadically. The public fascination with interstellar visitors demonstrated by media coverage of Oumuamua and 3I Atlas could be channeled into sustained interest in astronomy and planetary science if new objects appear frequently enough to maintain engagement without overwhelming audiences with technical details. International cooperation becomes essential for maximizing the scientific impact of increased discovery rates. No single country possesses sufficient telescope resources to conduct comprehensive follow-up observations of dozens of interstellar visitors annually. Success requires coordinated global efforts that share observing time, data, and analysis capabilities across national boundaries and institutional affiliations. The transition from individual case studies to population statistics will fundamentally change how we approach anomalous objects like 3I Atlas. Instead of treating each discovery as a unique puzzle requiring custom solutions, we'll develop standardized analysis pipelines capable of rapidly distinguishing between natural variations and genuinely extraordinary phenomena that demand special attention. But regardless of what the Rubin era reveals about the prevalence of unusual interstellar visitors, the current mystery of 3I Atlas demands resolution on its own merits. The evidence accumulated over months of intensive observations presents a compelling case study in how science approaches phenomena that challenge established paradigms while maintaining appropriate skepticism about extraordinary claims. Part 14. Alien Artifact or Cosmic Oddball. After months of intensive observations, spectroscopic analysis, and orbital dynamics modeling, we arrive at the fundamental question that has driven this entire investigation. What exactly is 3I Atlas? The evidence accumulated by some of humanity's most sophisticated astronomical instruments presents a complex picture that resists simple categorization, offering tantalizing clues that point in multiple directions while definitively confirming none. The naturalist perspective, embraced by NASA and many mainstream planetary scientists, constructs a coherent narrative from the available observations. 3I Atlas represents an interstellar comet with unusual but not impossible characteristics that can be explained through natural processes operating under exotic conditions. Its CO2-rich chemistry reflects formation near a carbon dioxide ice line in its birth stellar system, possibly around a different type of star than our Sun, or within a protoplanetary disk with chemical gradients, unlike those that produced our solar system's objects. The evolving coma and tail, structures captured in exquisite detail by Hubble and ground-based telescopes, demonstrate classic comet behavior, responding predictably to solar heating and radiation pressure. The transition from unusual anti-tail features to conventional dust-tail development follows established patterns observed in solar system comets under specific geometric conditions. The rising production rates of nickel and cyanide as the object approaches perihelion match theoretical expectations for increased sublimation due to enhanced solar flux. Most importantly, the apparent absence or extremely low magnitude of non-gravitational acceleration can be explained through natural mechanisms that don't require exotic physics or artificial intervention. If 3I Atlas possesses the anomalously high mass suggested by some analyses, 3.3 times 10 to the 10th metric tons, then normal outgassing simply lacks sufficient thrust to measurably deflect such a massive object. Alternatively, if its surface composition and rotation state produce unusually symmetric outgassing patterns, the individual jets could cancel each other's momentum transfer while still creating dramatic visual displays. This explanation requires no new physics, no unknown materials, and no unprecedented formation scenarios. Interstellar space contains objects with diverse compositions, thermal histories, and structural properties that reflect the wide variety of stellar systems and planetary formation processes operating throughout our galaxy. 3I Atlas represents the extreme end of this natural distribution rather than evidence for artificial construction. The speculative perspective, advanced most prominently by researchers like Abraham Loeb and echoed across various scientific forums and popular media outlets, argues that the accumulating anomalies resist natural explanation when considered collectively. While individual characteristics might be dismissed as unusual but plausible, their combination in a single object approaches statistical improbability that demands consideration of artificial origins. Active stabilization systems could explain the persistent absence of detectable non-gravitational acceleration despite clear evidence of asymmetric outgassing. Cold gas microthrusters, or reaction control systems, could counteract natural thrust vectors with precision sufficient to maintain trajectory stability while allowing controlled material emission for reconnaissance purposes. The engineering principles exist in human technology. The question becomes whether some other civilization has developed these capabilities to interstellar mission scales. The nickel without iron chemical signature, while potentially explainable through natural space weathering processes, also matches the erosion patterns expected from high-temperature nickel-based superalloys used in advanced propulsion systems. If 3I Atlas represents a reconnaissance probe experiencing operational wear, the spectroscopic evidence might document this degradation process in real time. The apparent mass concentration, inferred from outgassing analysis, could reflect artificial construction designed for long-duration interstellar transit rather than natural accretion processes. Objects built rather than born might achieve density and structural characteristics impossible for natural planetesimals formed through gravitational collapse and collision processes. Even the trajectory characteristics have attracted speculative attention, with some analyses suggesting deliberate navigation designed to optimize solar energy collection, maintain specific orientations relative to the ecliptic plane, and facilitate extended observation opportunities. While these patterns could represent natural orbital mechanics, they might also indicate intentional course corrections executed with precision that surpasses current human capabilities. The evidentiary standards for accepting artificial origins necessarily exceed those required for natural explanations, and current observations fall short of meeting these stringent requirements. Extraordinary claims demand extraordinary evidence, and 3I Atlas provides intriguing anomalies rather than definitive proof of non-terrestrial technology. Each unusual characteristic permits natural interpretations that, while requiring specific conditions or coincidences, remain within the realm of known physical processes. Yet the scientific method demands that we maintain intellectual honesty about the limitations of our theoretical frameworks. Our understanding of comet physics derives primarily from objects formed within our solar system under specific temperature, pressure, and chemical conditions. Interstellar visitors arrive from environments that may operate according to different rules, challenging our ability to predict their behavior using locally derived models. The distinction between cosmic oddball and alien artifact may ultimately depend on factors beyond the observational capabilities available during 3I Atlas's current apparition. Future discoveries of similar objects, improved theoretical modeling of exotic comet behavior, or more sensitive detection techniques for artificial materials and technologies could shift the evidentiary balance in either direction. For now, we're left with genuine uncertainty about phenomena that push the boundaries of established science while stopping short of revolutionary confirmation. This ambiguity reflects the authentic nature of frontier research, where the most interesting questions often resist immediate answers and demand patience, persistence, and intellectual humility from investigators seeking truth rather than confirmation of pre-existing beliefs. The resolution may ultimately come not from 3I Atlas itself, but from the broader context provided by future interstellar visitors and the advanced observational capabilities that will characterize the next phase of CON, our cosmic reconnaissance efforts. Part 15. The Masked Broadcast Theory, a message hidden in the coma. What if we've been asking the wrong question entirely? Instead of puzzling over why 3I Atlas shows activity without acceleration, perhaps we should be asking why any civilization would engineer such precise behavior in the first place. The Masked Broadcast Theory, emerging from the intersection of SETI research and advanced signal processing concepts, proposes that 3I Atlas isn't trying to hide its artificial nature, it's broadcasting a message using the most universal language available to any chemistry-literate species. This speculative framework reframes the central anomaly as intentional design rather than mysterious physics. The absence of non-gravitational acceleration, despite vigorous outgassing, becomes the carrier wave for a low bitrate communication system that assumes young civilizations will point their most sophisticated instruments at unusual interstellar visitors. Any species capable of spectroscopy would recognize artificial modulation patterns embedded in the natural chemistry of the coma, creating a communication channel that requires no prior knowledge of alien languages or technological conventions. The engineering elegance of such a system becomes apparent when considered from a cosmic perspective. Spectral lines represent universal physical constants that remain identical across all technological civilizations. Hydrogen emits photons at 21 centimeter wavelength, regardless of which species observes it. Carbon dioxide absorption features appear at the same frequencies, whether detected by human instruments or hypothetical alien telescopes. A modulation scheme based on ratios, CO2 to H2O abundance variations, nickel emission line, strength fluctuations, or subtle changes in isotopic signatures, would be readable by any civilization sophisticated enough to conduct precision spectroscopy. The mechanism could operate through what signal processing engineers call amplitude modulation of chemical emissions. Extremely symmetric outgassing maintains trajectory stability by cancelling thrust vectors from different surface regions, while microscopic adjustments to individual jet intensities create time-varying patterns in the overall spectral signature. The object maintains its gravity-only orbital path, while the chemistry tells a story that natural physics couldn't produce through random processes. Consider the potential encoding grammar hidden within months of accumulated spectroscopic data. Prime number sequences, embedded in the timing of intensity fluctuations, would immediately flag artificial origins to any mathematical civilization. Fibonacci progressions in line strength ratios would confirm intentional design rather than random chemical evolution. References to well-known cosmic constants, hydrogen hyperfine transition periods, the fine structure constant, or mathematical relationships like pi, could serve as universal Rosetta Stones that establish common ground between species separated by vast distances and evolutionary histories. The mysterious nickel without iron signature gains new significance within this framework. If standard comet chemistry produces both elements together, then selective enhancement of nickel emissions creates a deliberate contrast that highlights artificial manipulation. Tiny, controlled variations in nickel line intensity could function as the dots and dashes of an interstellar Morse code, with iron's absence serving to emphasize that the nickel variations represent intentional signals rather than natural abundance fluctuations. The antitail geometry observed during 3I Atlas's early approach phase could serve as punctuation marks separating symbol groups within the encoded message. As viewing angles change due to orbital motion, different portions of the expanding dust and gas coma become visible, creating natural breaks in the data stream that help distinguish between individual message components and continuous background chemistry. Even the early brightening event that first attracted astronomical attention gains new interpretation as an intentional hello tone burst designed to ensure early detection and comprehensive data collection. If a civilization wanted to maximize the observational baseline for their encoded message, they would need to capture scientific attention months before perihelion passage, when natural activity peaks might overwhelm subtle, artificial modulations with background noise. A serious decoding attempt would require systematic analysis of all available spectroscopic and photometric data, spanning 3I Atlas's entire observable apparition. Researchers would need to construct detailed time series from published spectra, normalizing for natural variations due to phase angles, heliocentric distance changes, and potential rotation periods. The challenge lies in detrending all expected natural drivers to reveal residual patterns that resist astrophysical explanation. The search would focus on non-astrophysical periodicities, prime-spaced intervals in emission line intensities, irrational ratio beats between different chemical species, or systematic variations that correlate with geometric factors in ways that natural physics wouldn't produce. Modern signal processing techniques, originally developed for extracting weak radio signals from cosmic background noise, could be adapted to search for artificial patterns buried within spectroscopic databases. Visual representation of such analysis might reveal spectrograms highlighting periodic beats in emission lines, followed by statistical grids showing prime number spacing that survives rigorous significance testing. If genuine non-natural cadences existed within the data, they would generate headlines across scientific journals worldwide, while triggering unprecedented international cooperation to decode the message. Content. Critical skepticism demands acknowledging that natural coma variability, instrument observing cadences, and observational gaps can create patterns that mimic artificial signals. Random chemical processes operating over complex three-dimensional gas flows can produce seemingly systematic variations that fool pattern recognition algorithms optimized for detecting order within chaos. Any claimed detection of artificial modulation would require statistical significance levels far exceeding normal astronomical standards. With independent confirmation from multiple observational teams using different instruments and analysis techniques, the temporal aspect becomes crucial for testing this speculative framework. If 3i Atlas truly carries an encoded message, the signal strength and clarity should vary predictably with viewing geometry and solar distance. Natural chemical activity intensifies as objects approach perihelion, potentially overwhelming subtle artificial modulations with increasing background noise. Alternatively, enhanced gas production rates might amplify the signal-to-noise ratio for artificial patterns, making them easier to detect during peak activity phases. The theory predicts specific observation windows where message detection becomes most feasible. Geometric configurations that optimize viewing angles for anti-tail features might also optimize signal reception for encoded chemistry. Spectroscopic campaigns timed to coincide with these windows could provide definitive tests of whether artificial patterns exist within 3i Atlas's chemical emissions. International coordination becomes essential for comprehensive signal analysis. No single observatory possesses the temporal coverage necessary to sample potential message patterns at adequate resolution across the entire apparition. Success would require data-sharing agreements, standardized reduction techniques, and collaborative analysis protocols that combine observations from multiple telescopes operating in different time zones and wavelength ranges. The implications of successful message detection would transform every aspect of human civilization overnight. Confirmed artificial signals from an interstellar visitor would provide definitive proof that technological intelligence exists elsewhere in the universe, while demonstrating communication methods sophisticated enough to bridge the gap between entirely different evolutionary paths. The content of such messages could reveal scientific knowledge, philosophical perspectives, or practical information about the cosmic environment that surrounds our solar system. Yet even negative results would provide valuable scientific insights. Rigorous searches that fail to detect artificial patterns would place important constraints on communication strategies employed by hypothetical extraterrestrial civilizations, while validating our theoretical understanding of natural chemical processes operating in interstellar comets. The methodology developed for such searches would prove invaluable for analyzing future anomalous objects as survey programs like Vera Rubin multiply discovery rates. The masked broadcast theory represents the kind of bold speculation that drives scientific progress by expanding our conception of what might be possible, while providing concrete predictions that can be tested against observational evidence. Whether it ultimately proves correct or misleads us down fascinating but incorrect paths, it demonstrates the intellectual courage required to grapple with phenomena that challenge our deepest assumptions about intelligence, communication, and our place within a universe that may be far stranger and more populated than we currently imagine. But if 3i Atlas carries encoded messages, perhaps that represents only the beginning of a much more complex infiltration strategy designed to seed our solar system with technologies too small and numerous to detect, using conventional astronomical methods. Part 16. The Decoy Shepherd Scenario. Microprobes in the Dust. The most sophisticated military strategies often employ decoy systems that capture enemy attention, while the real operation proceeds undetected through parallel channels. Applied to interstellar reconnaissance, this principle suggests a chilling possibility. What if 3i Atlas represents not the primary mission, but merely the conspicuous distraction designed to keep our telescopes busy, while the actual payload achieves its objectives through entirely different means? The decoy shepherd scenario proposes that 3i Atlas functions as an interstellar school bus rather than a lone explorer. Its primary mission involves drifting through our inner solar system while quietly dispersing a swarm of millimeter to centimeter microprobes disguised as ordinary comet dust. These microscopic payloads then spiral into carefully selected niches throughout our solar system, Earth Trojan points, lunar farside craters, upper atmospheric layers, where they can conduct extended surveillance operations using technologies too small for current detection methods to identify. The engineering requirements for such a strategy explain every anomaly we've observed in ways that natural explanations struggle to match. A decoy mission demands trajectory stability, with near-zero net, non-gravitational acceleration, to keep deployment calculations simple and predictable. Any random kicks from asymmetric outgassing would scatter the microprobe swarm across unpredictable trajectories, defeating the precision required for targeted infiltration of specific orbital niches. Symmetric outgassing that cancels thrust vectors while maintaining vigorous activity serves dual purposes within this framework. It provides the cover story of natural comet behavior that satisfies most scientific observers, while creating the stable platform necessary for controlled release of artificial payloads at predetermined times and locations. The visible coma and tail development provide perfect camouflage for microprobe deployment, since normal dust emission creates exactly the environmental conditions needed to hide artificial objects among natural particles. The deployment strategy would be invisible to conventional astronomical observations. Most microprobe releases would appear indistinguishable from routine dust liberation, caused by solar heating of volatile materials. However, a trained observer monitoring meteor databases and wide-field imaging surveys might detect subtle anomalies, unusually coherent particle streams with narrow velocity dispersions appearing at solar longitudes that don't correspond to known meteor showers. The mysterious nickel signature gains sinister significance within this context. Thin nickel-rich coatings on microprobes could serve as protective shields against ultraviolet radiation and particle bombardment during their extended cruise through interstellar space. When heated by solar radiation during deployment, these coatings would ablate and produce the characteristic emission lines observed by spectroscopic surveys, explaining why nickel appears prominently while iron remains below detection limits. The microprobes shed their protective skins as they activate, leaving behind the chemical evidence that has puzzled researchers for months. Target zones for microprobe deployment would be selected for maximum strategic value while minimizing detection probability. Earth-Sun Lagrange, points L4 and L5, provide gravitationally stable parking orbits, where objects can loiter indefinitely without requiring active station keeping. These regions offer ideal vantage points for monitoring Earth's electromagnetic emissions, space traffic, and technological development, while remaining essentially invisible to ground-based telescopes due to their angular proximity to the Sun. Lunar farside polar craters represent even more attractive deployment targets for advanced surveillance systems. The permanent shadow regions in these craters maintain extremely low temperatures that would preserve sensitive electronics indefinitely, while providing natural shielding from Earth's radio emissions. Microprobes landed in such locations could operate as listening posts, with direct sightlines to interstellar space for communication with their parent civilization, all while remaining hidden on the hemisphere of the Moon that never faces Earth. Upper atmospheric deployment offers possibilities for more active reconnaissance missions. Microprobes designed for aerodynamic flight could use Earth's mesospheric layers as temporary staging areas, employing atmospheric drag to adjust their orbital parameters while conducting detailed surveys of our planet's environmental conditions, atmospheric chemistry, and technological infrastructure. These objects would appear briefly in meteor radar databases before vanishing, mimicking the behavior of natural micrometeorites, while actually representing sophisticated reconnaissance platforms. The timing of this hypothetical operation displays troubling strategic sophistication. 3I Atlas arrived during humanity's most capable period of astronomical observation, when instruments like the James Webb Space Telescope, Hubble, and ground-based adaptive optics systems could provide detailed characterization of its properties and behavior. Simultaneously, a proliferation of small satellites, radar networks, and citizen science monitoring systems creates an unprecedented sensor environment that could potentially detect microprobe deployment if anyone knew what to look for. A paranoid interpretation suggests that advanced civilizations might deliberately time reconnaissance missions to coincide with target species' technological adolescence, the period when they become interesting enough to study. but remain too primitive to mount effective defenses or countermeasures. The current moment in human history, with our expanding space presence but limited deep space monitoring capabilities, could represent an optimal window for conducting detailed surveys of our civilization. The breadcrumbs that would confirm this scenario should already be appearing in various databases if the timeline assumptions prove correct. Meteor radar networks worldwide continuously monitor the upper atmosphere for natural debris, creating detailed catalogues of particle velocities, arrival directions, and chemical compositions. Anomalous microstreams, with trajectories that trace back to 3I Atlas's position during specific time periods, would provide smoking gun evidence for artificial deployment events. Wide-field astronomical surveys designed to search for asteroids and comets also maintain archives of transient detections that could harbour evidence of microprobe activity. Brief, point-like sources that appear and disappear in Lagrange point regions over periods of days or weeks might represent microprobes adjusting their positions or conducting active sensor sweeps that temporarily increase their brightness above detection thresholds. The citizen science community possesses distributed monitoring capabilities that could prove crucial for detecting such subtle evidence. Amateur radio meteor scatter enthusiasts operate forward scatter detection systems capable of identifying particle streams too faint for professional radar networks. Amateur astronomers with wide-field imaging capabilities could coordinate search campaigns targeting Earth Trojan regions during optimal viewing conditions around new moon phases when sky backgrounds reach minimum levels. Falsification of the decoy shepherd scenario could proceed through systematic searches of existing databases combined with targeted observation campaigns. Meteor databases spanning decades of observations should reveal no coherent microstreams with chemical signatures matching 3I Atlas's unusual composition if natural explanations account for all observed phenomena. Focused surveys of Lagrange point regions over extended time periods should detect nothing above statistical background levels if no artificial objects occupy these gravitationally stable zones. Perhaps most definitively, high-resolution imaging that constrains 3I Atlas's nucleus size and mass could rule out its ability to carry significant artificial payloads. If the object proves smaller and less massive than required for housing and deploying thousands of microprobes, the scenario collapses under its own logistical requirements. The implications of confirming microprobe deployment would dwarf even the discovery of encoded messages within 3I Atlas's coma. Active surveillance of our solar system by artificial systems would represent not merely first contact with extraterrestrial intelligence, but evidence of ongoing intelligence-gathering operations that could have profound implications for planetary security and human civilization's future development. Detection of even a single coherent microstream with chemical hints that echo 3I Atlas's unusual composition would trigger emergency sessions at space agencies worldwide, while fundamentally altering humanity's perception of our cosmic isolation. The confirmation that we exist under active observation by entities possessing interstellar travel capabilities would force immediate reconsideration of every aspect of human expansion into space, from planetary defense priorities to diplomatic protocols for potential future contact scenarios. Yet, like all extraordinary claims, the decoy shepherd scenario demands extraordinary evidence before acceptance. The difference between paranoid speculation and legitimate scientific hypothesis lies in the quality of predictions, the rigor of testing methods, and the willingness to abandon attractive theories when confronted with contradictory data. Only systematic investigation can determine whether 3I Atlas represents a cosmic oddball worthy of scientific curiosity, or the advance guard of an intelligence that has been watching us far longer than we've been watching the stars. The next few months will prove crucial for testing these speculative frameworks, as 3I Atlas approaches perihelion and begins its journey back toward interstellar space. Whether it leaves behind only scientific publications and theoretical controversies, or evidence of technologies that transform our understanding of intelligence in the universe, may depend on how carefully we examine the subtle traces it deposits in the databases and detection networks that chronicle humanity's first tentative steps toward becoming a spacefaring civilization ourselves. Part 17. Closing Reflections. In the end, 3i Atlas forces us to confront a fundamental paradox that cuts to the heart of how we understand the physics governing small bodies in space. Here is an object displaying vigorous activity, visible outgassing, evolving tail structures, rising production rates of multiple chemical species, yet producing little to no measurable acceleration, according to the precision astrometric measurements that form the foundation of modern orbital dynamics. This contradiction between apparent cause and absent effect represents either a significant gap in our theoretical understanding or evidence for phenomena that operate outside conventional physical frameworks. The current best-supported scientific picture places 3i Atlas firmly within the category of natural phenomena, albeit at the extreme edge of what we've previously observed or predicted. This interstellar visitor carries the chemical fingerprints of formation in an environment, unlike our solar system, possesses unusual composition, dominated by carbon dioxide rather than water, and exhibits the mysterious nickel without iron abundance pattern that challenges conventional models of metal emission from comet nuclei. Its apparent mass, concentration and symmetric outgassing patterns provide plausible natural explanations for the missing non-gravitational acceleration that has captured scientific attention worldwide. Yet acknowledging the spark of anomaly hunting that drives scientific discovery, we must recognize that 3i Atlas has already expanded our understanding of what comets can be, regardless of whether future observations confirm natural or artificial origins. The object has forced improvements in theoretical models, observational techniques, and analysis methods that will benefit the study of small bodies throughout our solar system and beyond. It has demonstrated the value of rapid response observational campaigns and international cooperation in extracting maximum scientific return from brief encounters with interstellar visitors. The educational and cultural impact extends far beyond professional astronomy. 3i Atlas has captured public imagination in ways that highlight both the wonder and complexity of scientific investigation. It illustrates how genuine research operates at the boundaries of knowledge, where uncertainty and speculation play essential roles in advancing understanding while maintaining appropriate standards for evidence and proof. The object serves as a perfect case study in how science approaches potentially revolutionary discoveries, with excitement tempered by skepticism, curiosity balanced by rigor. Looking toward the immediate future, the perihelion passage scheduled for late October 2025 represents our final opportunity to resolve the central mysteries surrounding this enigmatic visitor. Enhanced solar heating might trigger new activity patterns that finally produce detectable acceleration signatures, confirming natural explanations through direct observation of the rocket effect in action. Alternatively, persistent dynamical stability in the face of intensified outgassing would deepen the anomaly and strengthen arguments for exotic explanations. Spacecraft observations from Mars orbiters and other deep space missions could provide unique viewing angles impossible to achieve from Earth-based telescopes. High-resolution imaging might finally resolve the nucleus itself, eliminating uncertainties about size, shape, and surface properties that currently limit our ability to distinguish between competing theoretical models. Precision spectroscopy during peak activity could reveal isotopic signatures that definitively establish natural versus artificial material sources. The broader implications ripple outward from this single object to encompass fundamental questions about the prevalence of life and intelligence in the universe. If 3i Atlas ultimately proves natural in origin, it expands our catalogue of exotic phenomena that operate within known physical laws while challenging our ability to predict and explain natural processes. If future evidence supports artificial origins, it would represent the most significant discovery in human history, confirming that we share the cosmos with other technological civilizations. The statistical context becomes crucial for understanding the significance of any conclusion we ultimately reach. 3 confirmed interstellar visitors in 8 years, with 2 displaying highly unusual characteristics, suggests either remarkable coincidence or systematic differences between objects formed in our solar system and those arriving from interstellar space. The upcoming Vera-Rubin era promises to transform this tiny sample into comprehensive population studies that will reveal whether anomalous behavior represents rare exceptions or common characteristics of interstellar visitors. International cooperation and technological advancement will prove essential for maximizing our ability to study future discoveries. The brief visibility windows of interstellar objects demand rapid telescope allocation, immediate spectroscopic follow-up, and real-time analysis capabilities that push current observational infrastructure to its limits. Success requires sustained investment in detection systems, analysis methods, and theoretical frameworks capable of distinguishing between natural variations and genuinely extraordinary phenomena. Perhaps most importantly, 3i Atlas reminds us that the universe retains the capacity to surprise us. Despite centuries of astronomical observation and decades of sophisticated space missions, we continue encountering objects and phenomena that challenge our theoretical understanding and force us to expand our conception of what's possible. This intellectual humility, the recognition that our knowledge remains incomplete and our theories remain provisional, represents the essential mindset for conducting honest scientific investigation at the frontiers of discovery. Whatever 3i Atlas ultimately proves to be, natural oddball or artificial artifact, it has already secured its place as the most scientifically important interstellar visitor since Oumuamua and Borisov. Not because it provides definitive answers to the questions that drive our curiosity about life and intelligence in the universe, but because it forces us to ask better questions, develop better tools, and maintain better standards for evaluating evidence that might transform our understanding of our place in the cosmos. The mystery continues, the observations continue, and our quest to understand these cosmic messengers carries us ever deeper into questions that probe the very nature of reality itself. In the end, that journey of discovery might prove more valuable than any single answer we uncover along the way.